So, just wait. All right. So I'm going to start. Right. So hello, everyone. I'm Anderson Vulto from the Brazilian team from Unicamp, and I'm here to show our solution for problem number 10, rolling pasta, and showing some our results. So the problem statement is when spaghetti is rehydrated on a wet cloth, the noodles gradually acquire a curvature that persists even when they're taken out to dry, and they still start moving with some velocity. So we are asked to investigate the noodle movement and its shape dynamics, and also see if the phenomenon is present for other common pasta shapes, such as linguine, bucatini, or lasagna. So first of all, how is pasta made? First of all, we got the durum wet, passing through a milling purification process. Then we got the semolina dough, which contains 12% protein and 70% carbohydrates, passing through a water mixing at 40 degrees and through a vacuum chamber and extrusion process, drying the water from 31% down to 12%. And then we got the edible pasta. So the main features of the pasta we can consider are the proteins and the carbohydrates. For the proteins, we got the gliadin and glutenin chains, which contributes to the dough extensibility and dough elasticity, and they combine together into gluten. And gluten gives the pasta its viscoelastic properties. So the carbohydrates, the main carbohydrates are the starch granules, and the starch granules are embedded in protein matrix. So we can see here in the picture some granules embedded in the protein matrix. When a starch is in contact with the cold waters, the granule swells 10 to 20%, parting from the helium, which is the center, and going out like this. And the swelling is a two-stage process. The first process is a radial expansion, as we saw in the previous slide, and form a flattened disc. And it's followed by a tangential expansion, turning into these granules. So this is the phenomenon. We record a 6-hour time lapse, 1 frame per minute, and you can see there is a lot of dynamic going on here with a lot of different length of pasta. So the main physical mechanism we are approaching is that the uneven swelling is the main source of the displacement, because the net displacement is perpendicular to the surface, and the bending points in the bending points are in the direction of the lowest expansion rate, of course. So the first experiment we did was for the lasagna displacement. So the hypothesis here is that if the diffusion inside the pasta is low enough, there would be two interfaces, and the displacement points are in the expected direction, as you can see in this scheme. We see the wet cloth here, and then a dry cloth here, and it should bend upwards, and that's exactly what happens. The pasta bends upwards from the region that's wet. So for the spaghetti displacement, we expected the same. So the start swelling in cold water should lead to upper bending as well. And so for that, we create two interfaces, one dry spaghetti interface, which you call A, and a wet spaghetti interface, which is B. So we expect that it bend upwards into the tips because of the uneven swelling. So this GIF shows that exactly what happens. And then we can compare the diameters and see the uneven swelling occurring differently in the wet and dry spaghetti regions. So for the dry region, which is up here, you see that the displacement of the diameter is much less than the wet cloth interface, in the wet spaghetti interface. Sorry. So for recording this type of experiment, we use a setup with a magnifying glass with a focal distance of 5 centimeters, and put a cell phone right into it, so we could record and take 2 pictures with a resolution of 9 microns per pixel, using a coin as reference. So the diameter increasing, basically proving the same point here with a consistent result. We can see that after some time, the diameter increased for about 25% in the vertical direction. So how to account for the horizontal displacement? So mainly we are using the hypothesis of the bending flip dynamics, because you can see when the the uneven swelling occurs, the pasta bends upwards, it creates a potential energy, and then it would flip because it would transform the potential energy into kinetic energy. And there is some rolling as well because of the arbitrary asymmetry caused by the uneven cold soaking of the water, and this may cause rolling because of the torque formed into the pasta. So here's a time lapse of the bend and flip and rolling. So what have we learned? Going back to the first time lapse I showed you, where there was a lot of dynamics we could not explain very well. Investigating with our approach, we can see that a lot of bending, moving, bending, flipping, and rolling process that cause the movement in the plane direction. So how does the length relate to displacement? We can see that's a lot of pasta with different lengths, and as the length increases, also the horizontal displacement increases because it would bend more and would flip more over and over. So it should go a lot more with a higher direction. So time lapse close up, so you can see that pasta trains cross over one another, and you can see it's bending and flipping very well. And so comparing some kind of pastas, for the common pasta, which is the gluten with gluten pasta, we got an average displacement using these three pastas of 3.6 centimeters with a deviation of 0.9. And then for gluten-free pasta, which contains 34% lower content of gluten, we see that the displacement it's 8.6 centimeter with a 1.7 deviation, which is higher than the gluten spaghetti, and it's what we expect. And we can also show some average angle alpha, which is the angle between the center of the spaghetti, the line that crosses the center of the spaghetti and to the tip. So this should be angle alpha right here. And the angle also increases a lot for the gluten-free pasta. It goes up from 8.2 degrees for 20.6 degrees for the gluten-free. And we also saw the phenomenon happen with the bucatini pasta, which is just spaghetti with some hole passing through the pasta, and this hole barely makes a difference because it also has low internal diffusion, so we can observe the bend and flip. And the linguine, it tip bends upwards, but the flipping is so much more unlikely due to the fact that the pasta is flat and it has no opening to rolling. So in conclusion, the starch granules in pasta cause it to swell when exposed to cold soaking. Uneven swelling causes the pasta to bend. Horizontal displacement is mostly due to the bend and flip model, not rolling, because the rolling is accounting to arbitrary asymmetry of cold soaking. And the different types of pasta changing the phenomenon we observed it in gluten-free pasta, bucatini, and the linguine. So that's it. Thank you.
Thank you very much. Now, French team, you have time for asking your clarifying questions.
Oh, sorry, let me...
I don't think it was, yes.
Right.
Sorry. Sharing, yeah.
Wait, can I...
Or we have terrible echo.
Can I see the slide 11, please?
11, okay.
Can you, I don't know if it's a technical question, but I do not really understand your diagram at the upper left, the right section of the slide.
All right, so you can imagine the experiment here, right? So this region is a wet cloth region, and this is a dry cloth region. So you can see here, this is the wet cloth, and this is a dry surface. Okay. It's clear?
Yes, thank you very much. It was very clear. So can I see the slide 15, please?
Of course.
So you just introduce an optical.
Yeah, just to amplify the observation of the phenomenon. It's not a complex mechanism.
Okay, thank you. Can I see your slide about the asymmetry of the humidification? Yes. So can you clarify this hypothesis? I don't know, again, it's a technical question.
Okay, so we didn't quantify it, but it was observed that the pasta should soak in an even way because of the starch granules. The starch granules are not distributed in an uniform way, as we show here. So in a cross section of the pasta, you should observe these granules in random positions. So because they are responsible to soak the water, you could not see that the water would be absorbed in an even way. It's uneven, not even way.
Oh, okay, thank you very much. Can I see the slide, I don't know, 42, please? 23, sorry.
23, okay.
Okay, so you just measure how did you measure the average distance about all the spaghetti axis?
Right, is the distance of the center of the pasta. So this red line here, it's over? Can I finish
yeah, finish fast.
Okay, yeah. So this red line here represents the pasta in the initial position. So we got like a vector in this from the center of the pasta to the position we got after some time.
Okay,
great. Thank you very much.
To investigate the pasta shape and curvature during the time of humidification, and they study it very well. Along that, they also study microscopically the shape and structure of the pasta. That was very interesting. They also study the pasta movement, but I think maybe partially because they only concentrated their study on the edges of the pasta and not on the central part of the pasta. And they really have a lot of pasta. They tried a lot of pasta. So I think it's a very good point. So they changed the type of the pasta and also the shape. So as I said, they have a really good study of the structure of the pasta, and I think they have a good qualitative but understanding of the bending mechanism. And as I said, also they studied various types of pastas. Like I think it was interesting because maybe they could have changed diffusion characteristic, the characteristic of the diffusion of humidity inside their pasta. And also, I think they have a very good experimental setup. So it was a very good idea to magnify what they observed in order to have a precise measurement of the expansion, and so to have a measurement of the humidification of their spaghetti, because it's a key point in this problem. What can be improved? So the Young modulus of pasta change a lot with humidity. It can change like a factor of 100, and it can affect a lot the movement of the pasta, because if you have a very low Young modulus, the pasta will be highly deformable, and so maybe you cannot have the same bending mechanism, etc. There is two important parts in the problem. So it's the humidification of the pasta, but also the drying, because when the edge bends, the pasta dry because they are no longer in contact with the wet cloth, and so maybe you do not study it, but maybe it was an important part of the experiment. You try different type of pasta, but you do not change the diameter of the pasta, because it can be interesting because it can change the humidity gradient inside your pasta. One maybe what was lacking in your experimental setup was the control of the humidity of your wet cloth, because you say the humidification is a key parameter, and you did not try to control it. So maybe you can improve this experimental setup. And also maybe it will be better to have a more quantitative explanation of the phenomenon. So to discuss, maybe you can talk a bit more about what changes the type of pasta, what can change the curvature of the pasta, maybe, or the different movement. How maybe you can improve the control of humidification and drying, that are the two key physics phenomena that are present in this experiment. And I see in your video that you have more complicated movements. So we can talk about it if you want, because I see that there is not only bending of the edges and you only talk about it. So if we want to expand our knowledge, maybe we can talk about it. And maybe we can also talk about the time scale of the problem. So because humidification is a key point, maybe you measure the diffusion. Maybe we can talk about the time scale, like the diffusion time scale and drain time scale, in order to see if it's coherent with what we observe in our experiments. So I don't know with what do you want to start?
So we can start talking about the humidification. I think it's a very important parameter because it affects the velocity that the pasta soaks. But there's a problem because the humidification has to do with the temperature, and the pasta, because of its composition in the protein matrix, you have to be aware of the temperature and the amount of water that you're soaking, because if not, you would not have movement at all. You would like bend in the same place and just not have you would not have the structure to bend and flip, right? So you would cook the pasta basically.
Yes, I agree. That's why I talk about Young modulus. But do you have a quantitative measurement of the humidity ratio in like in wet clothes? Because
no, we didn't do that because I think we should had a more sophisticated apparatus, and at home because of the pandemics we didn't have this kind of apparatus to control the humidity.
Okay, and do you think the fact that because your wet cloth is drying in time, yes, do you think it has an influence on the movement?
It has some influence, but it's not a main factor to make the pasta have a lower displacement, for example, because we had a wet cloth wet enough to move the pasta for some really good time, and it moves real slow. So you get about like 10-hour footage because of the movement. You can see it's still moving after 10 hours. So
yes, that's what I mean, because it's very slow. The humidity in your wet clothes can change. That's why maybe at late time you have not the same behavior at like early time. So that's why.
Yeah. So if you have less wet cloth, it should soak real fast, right? At room temperature, and so you would have a lot less movement. But that point is a lot is a lot of variable, because again, how can we control how wet is the cloth and how wet is ideal to move pasta some point, right?
Some ventilation, I don't know, because with ventilation you can maybe control the ratio in time of your wet cloth, or
yeah, maybe I agree with you. Yeah, maybe. So, about the Young modulus, I thought it was really interesting that you raised this point. It should be a parameter that we could study, but it would depend on the pasta composition, right? Yes. So you can make pasta with whatever composition you want, mixing the proteins and carbohydrates, right? Of course, you have a limit, but you could do 40% or 40% carbohydrates and 6% proteins, and it would have it would have a higher Young modulus, for example, because of the elasticity would be bigger.
So in your experiment, like you try with different pasta, like without gluten, and so yes, can you do the interpretation with this parameter for the measure the average displacement after like 10 hours when your clothes was completely dry. I don't know. And right, can you relate maybe the Young modulus with what you measure? Can you show your slides so it's maybe easier?
Yes, we could relate to a Young modulus, but we didn't measure this quantity because well, we just didn't measure this quantity. Instead, we did measure the. Are you seeing the slide?
Sorry?
Yeah.
Are you seeing the slide? My
Oh, yeah,
slide?
perfect.
Okay, so instead of measuring the Young modulus, we measured another quantity that's this angle we call alpha, which is the angle between the center line of the pasta, as I said, to the tip of the pasta. So it's the bending angle, right?
Okay, and can you maybe qualitatively relate this angle with the type of pasta you use in your experiment?
Yes.
We can now let team members to join the discussion.
Yes, we could probably relate to quantitatively to a kind of pasta, but we just compare the gluten-free because of the protein content, right? So because we know the protein content of the gluten is 34% lower for the gluten-free pasta, we could see that you would have a variation in the elasticity of the pasta, right?
Yes.
And its toughness too. So it would bend more and would move more.
Okay. In your
Philip had a question.
Yes, I was just going to comment, but Anderson ended up making a comment. I would. It's okay. You can go on.
Okay, far away.
In your picture, like the middle pasta, the second one, when we start from the first, you see that the pasta is not evenly adherent to the wet cloth at the end. So, do you think that can change your theoretical model because you only assume that the edges were working? Maybe you can show a slide with your theoretical model.
So we don't have a mathematical formulation for this. We did an empirical analysis of what the bending.
No, just because you assume only that it was the edges, but in your at the end of the month, actually. So
you're talking about the physical.
Yes,
mechanism? All right.
Yes, you only study the edges, but you think because at the end of your experiment, your pasta was not evenly adherent to the wet cloth. You mean there is curvature even at the center of your pasta. So maybe do you think you can explain this phenomenon with the same mechanism?
Maybe I can clarify it. It's the very process of bending and flipping changes the points of contact, right? So if you bend a little bit and then you fall to the side, then maybe you have a different point in contact, and that causes the wave. I think you're talking about the waviness we observe, right? Maybe that's the best video to see it.
Yeah.
You can see you can see by the shadows that there's always some bending relative to the surface. And what happens is that sometimes even the pastas cross over each other, right? That indicates that they are not touching the surface at the edge, and so you can have a point of contact with the cloth that's not at the edge, right?
Yeah.
But it
Another
will behave like an edge.
Another problem with the cloth is that it would not be always flat. It should have some defects on its surface. So when the pasta starts to moving and passing through it, you can see that you would change the point of contact too.
And so what was the repeatability of your experiment? Did you try maybe because you did not use the same wet cloth at each time because you did not control humidity? So was your experiment repeatable? That means with two different experiments you obtain the same results, or can it differ?
It differs all the time because we controlled the amount of water we were leaving on the cloth, right? But we cannot control how the soaking will occur on the pasta because we cannot control how the starch granules are going to interact with the molecules of the water they are soaking, and so how their swelling will affect on the movement, right?
Yes,
so
but
it's
maybe I think I got you were concerned about the replicability of the wet cloth, right?
Yes,
what we did there.
Yes,
okay, go on.
Oh, sorry, go on. Sorry.
Okay, just what we did to ensure replicability, we were always using the same kind of cloth and always submerging it completely for a given amount of time and then taking it out and putting in the same kind of environment. So that's to ensure replicability. It's mostly the same type of cloth.
So you just tell me that this experiment is a little bit probabilistic because you cannot obtain the same result twice. But did you make like average and have like a variance in your model? Because maybe if you done it this a lot of time, you can have a distribution or.
Well, we showed the standard deviation, for instance, for the amount of total displacement measured, right? So, for instance, one of the most important results, I think, is the fact that gluten-free pasta and pasta with gluten have very different average total displacements, and we explained that in terms of the protein content, which contributes to the stiffness, which changes the amount that the pasta is able to bend and therefore flip and displace, right? So that's the statistical treatment we showed. It's right there in slide 24.
My question is that you have chosen this angle to be your quantity to measure. Have you considered fixing a center of or one of the ends of this spaghetti and measuring with a fixed point?
No.
What do you expect? What do you expect to see if you fix one of the points center on the or the end? What difference do you expect to see?
Okay, the first difference is that if we fix the center of the pasta in a weft cloth, you should see a more even distribution of the water because it's fixed, and because it will not displace through the plane. You should have a point where you will not soak water anymore, right? Because you will not have the surface in contact, only the center, and the center will soak all the water.
Can I add something? Sorry.
Do you want to hear the answer from the team member?
Yeah, if we have time, of course.
Yeah, quickly, we actually tried this. We just put one end of the spaghetti in a dried place and the other end in the tip of the cloth. And it happens exactly what Anderson described. So you have dries a little bit and then tips over, and the other end remains fixed, right? Because it's completely dry. But soon enough, the part that's in contact with the cloth will be completely, will have bent all the way through.
It's different experiment. I'm not saying about dry end, but let's give other jurors possibility to ask question.
Yeah, thank you. Severian, can you ask your question now?
Sure, thank you. I'm just wondering, so you mentioned that in your opinion, the protein content is an important parameter to control the deviation. So I'm just wondering if you had a chance to try another type of pasta, for example, not only gluten-free, but also the one which is produced with eggs, which should have by about 15% higher value of protein content, and then it would give by far larger spread from the bottom, let's say, to the top concentration, and if the effect is even more pronounced. Thank you.
Right. Thank you. Sorry, I missed the question.
I'm sorry, no worry, I'm happy to repeat. So basically, my question is, one of your main conclusions is that protein content affects considerably the highest deviation. So I think there is one common pasta which is produced with high amount of eggs in it, and then it has about 15% higher content of protein. And then the question is if you had a chance to check something like that to see if the effects are even less pronounced.
Yes. So, if Felipe wants to answer.
I could just comment that the pasta with gluten that we checked has the egg coating, right? It said that to increase protein content and make pasta more nutritious. So in fact, the gluten-free which we used has no egg content, and the with gluten has some egg included in it. So I think that the protein difference which we mentioned already included the 34% protein content is already in part due to this presence of eggs in one of them. Okay, it's an important point.
Okay, thank you.
Great, thank you for the comment. Vladimir, can you ask your question now?
Yeah, thank you. Could you please show slide 11?
Of course. Here?
No, with the plot. Okay, I'm sorry.
Maybe not 11.
Ah,
yeah.
right.
With the plot on the length.
The plot.
Uh,
Okay.
the speed
Okay.
here. And okay, I am a little bit surprised that you have no errors here, no any crosses. And the question is that, as I understood, your process is largely random. And sometimes, okay, pasta bend in one direction, sometimes in other. And do you displacement is so even and so continuous, or probably you just forgotten to make more measurement and to obtain some errors?
Right. So first of all, actually the errors exist, but they are really small for the
But what about multiple tries? Have you tried to make the same experiment but multiple tries in order to obtain these?
Yeah, I agree. We should do multiple tries. We should do. It would be a more statistical problem, right? Because we could have a lot of pasta like in this time lapse we did, but moving in different directions and got different direction vectors and do a kind of distribution with the length of the pasta. I agree.
Okay, yeah, and also the motion is not continuous, and so the error will increase. And the second question, small question, is about that you have more displacement for a larger pasta. And does it hold till the infinite length? The question is both to the reporter and opponents.
Oh, okay. This is interesting. When you would have a pasta with infinite length, you should expect to bend in the tip, right? But where's the tip? So it would soak water like almost forever. we should say like that. And so we would expect a bending some point, sometime, because this infinite is not the real infinite, right? That we could say real big, but in some point it would bend and flip and roll, and we could see some displacement. But after a long time and after a lot of soaking.
Can I answer, please?
Yes,
Yeah.
please answer.
Okay, so if you use just an infinite wet cloth and you make the pasta roll, assuming the humidity in the wet cloth is constant, the pasta will certainly roll, but after the time, its humidity will be too high, and so it will not move anymore because it's too deformable. So what you have to do is to control the ventilation, and by controlling the ventilation, you increase the rate of drying, and with that, you can obtain a pasta with a average humidity that is approximately constant in the pasta, and theoretically, it can roll forever.